Hello everybody, Oxford College Physics, Justin Miller here. We got some work to do, so let's just get started. Today's segment we're going to be looking at diffraction and Young's double-slit experiment. So first off, let's just start off with diffraction. Diffraction is a wave property that ultimately says that waves have a tendency of spreading out. You don't just want to travel in a nice straight line, you want to diverge as they move through, well, whatever material they're moving through, or free space in the case of light in a vacuum. We're focusing our attention on light right now, but that's basically that. So diffraction is the tendency of light to spread out, say outward, as it propagates. What we can have is ultimately that light can bend around edges because of this tendency to spread out. So ultimately, this can be utilized to produce what are known as interference patterns. We know that light is a wave and that waves can interfere with one another. So if we have two sources of light that occupy the same space at the same time, it is possible that we can witness some interference patterns due to them overlapping, due to their waves producing constructive and destructive interferences. But there's a certain criteria that needs to be met in order for that to happen. Well, in order for us to produce it, we'll say. So, two sources. Monochromatic. Mono, meaning one color, so one wavelength. Two sources of monochromatic light. Begin with a constant phase relationship. Some location. And overlap at another location. One may witness an interference pattern. Due to destructive and constructive interferences occurring. Occurring. So this brings up what is known as Young's double-slit experiment that ultimately first demonstrated this. What Young did was ultimately produced two coherent beams of light, but two coherent light sources, in a sense, and we have them diverge outward from a certain point and captured an interference pattern on a screen. So basically, what he did was take two slits, two thin slits separated by some distance. So this is a slit, thin slit. And we had some source of monochromatic light ultimately directed upon these thin slits. Now, what was done was took a nice little screen over here in order to observe the light sources as they went through here, and ultimately found some pretty interesting things. So if light wasn't a wave, if diffraction did not occur, if there wasn't this spreading out of light, we would expect that the beam that goes through this location just produces a nice bright spot right there. And the beam that goes through this location, or the light that goes through this location, produces a nice little beam and produces a little bright spot right there. So we would think that we get these two bright spots here and here. But that's not what was observed. What was observed was something much, much more complex. There was a fundamental, really bright spot right in between where we would think the two main bright spots would be. And there's a succession of a whole bunch of striations of bright spots and dark spots, bright spots and dark spots. And that could only be explained with constructive and destructive interferences occurring due to, well, some sort of wave properties. So this ultimately was something that demonstrated that light had wave properties associated with it. So what it comes down to is that as light exits these little slits right here, it has the tendency of spreading outward, diffraction occurring. And ultimately, it's like these little slits here act as sources of spherical wavefronts. So this is going to look messy because this is hard for me to draw out without taking a whole bunch of time, but ultimately, we've got this slit here, this slit here. I guess I should still use purple. One wavelength. Act as now sources of spherical wavefronts. So we've got that light starts coming out of this. Spreading outward as it's going out. And these wavefronts represent like the peaks in the actual wave themselves. The separation between these is supposedly a wavelength of the wave itself, which is hard for me to preserve there, but these should all be equally spaced. But this is what we end up getting. We get that because these started in phase like this, as they spread outward more and more, we get that they start overlapping. And if you notice, there's this point right down this middle where they're going to continue to overlap. I'm going to stop drawing it out because it starts again to get really, really messy. But there's this point where, straight down in between, they're always overlapping. That is that these waves along this position right here are completely in phase with one another. So what do we get if we add two waves together that are in phase? We get a doubling of the amplitude. That's right. So we get some bright spot right here. Well, that's the one that's right down the middle that's observed. But that's not the only location, because look it, if I keep extending these out, they're going to start overlapping over here as well, and here, and here, and there's going to be another line that comes down here, which produces another bright spot. That all along that path we have constructive interference. Another one up here. And ultimately there's going to be a bunch of them. Locations where we get these bright spots. There's also locations where we get dark spots, where we have these wave fronts connected directly between two other wave fronts from the other source. That's destructive interference. We've got a peak and a valley, in a sense, regarding the wavelengths interfering with one another, collapsing. And what do we get? We get nothing. We get a dark spot. And there's specific angles at which those dark spots will occur. So what do we get out of this? We get an interference pattern. So I'm going to open up a little demo, in a sense. Kind of be able to see it. I'll take a picture of it, put it in here too, but only just to see. So got a little laser right here. It's not on, thankfully. And then I've got this little wafer right here that has some really thin slits separated by really, really small distances. There's 3 different sets of them, double slits, where one of them is separated by, it looks like about a millimeter, maybe half a millimeter, quarter millimeter. So they're really, really finely spaced. And what we want to look at is some light here that strikes those. There we go. And produces a nice interference pattern. All right. Things kind of blinking a little bit, but we've got the light striking these, and right there, you should notice that there's this big bright spot in the middle, and as you'll see in a nice picture, there's this striation. There's these alternations of bright spot, dark spot, bright spot, dark spot that span out across this way. So I could actually take this out of the way, and look what happens. We just get that one bright spot right there. When I put it back in, here it comes. That was off the edge, that's kind of neat. Put it back, and there it is. So that is the one with the largest spatial separation of the slits. I could put one on that's smaller. And again, we still get this striation now. I'll take, again, some pictures of this because there's a really, really fine pattern in there. Really, really well-defined and very, very closely spaced separation between the alternation of the dark and the bright spots. And likewise with this, there's a whole bunch of little striations inside these little pockets here. And that's interference. That's what we've got. So that's what we want to be looking at, and we want to come up with some sort of model with respect to being able to depict and ultimately know what sort of diffraction pattern are we going to get, and that's pretty much that. So let us go ahead and take a look at this. So what we are going to do is go ahead and think about how we're going to get the bright spots and the dark spots. So bright spots have to be produced by constructive interference. Dark spots have to be produced by destructive interference. And because we have monochromatic light of one wavelength, we have one wavelength for one source is the same for the other. So what we can start to look at is what criteria do we need in order for constructive or destructive interferences to occur based upon the wavelength of the light. So take this. Can take some screen over here, put it kind of close. We can look at what we've got going on. So if the light waves from the sources meet in phase, we get constructive interference. Which gives us a bright region. Let's just focus on constructive interference right now and think about what that means. Well, IGH2. Well, that means that, again, if they overlap in phase with one another, peak, peak, valley, valley, anywhere in between, as long as they're in the same phase at that location, then we get ourselves a bright spot. So let's think about a couple things here. I'm going to put this line, which I like to call like a principal axis, that is directly in between these two slits here, just so we can make some sort of generalization of how to measure things. So we'll measure everything relative to this line right here. Again, call it principal axis, just to call it something. So where is constructive constructive interference going to occur? Well, because they start in phase here, and we want them to end in phase over at the screen, it comes down to the paths that they have to travel, the lengths that they have to travel, lengths through space. So if they go through the same number of oscillations, in terms of the same number of wavelengths to reach a spot, they will be in phase, and we get constructive interference. There's only one spot where they will undergo the same number of oscillations in reaching it. And that is the one spot that they travel the same distance to. That will be, well, oops, we'll use this one. That will be this location right here. The distance from this slit to this location, and the distance from this slit to this location are the same distances. That means that the oscillation the number of oscillations is the same. So we've got same number of oscillations, which means then the same number of wavelengths, which means then that they meet in phase. What do we get? We get a bright spot. That's the only location where they can travel the same distance. But what else do we need? Well, we don't need that they necessarily travel the same distance. We only need that they're in phase with one another. So what if one travels one more wavelength than the other? If it travels exactly one wavelength more, or two wavelengths more, or three wavelengths more, what's going to happen? They're still going to be in phase. One's just been ultimately shifted over by a wavelength, two wavelengths, an integer multiple of wavelengths relative to the other. They still meet in phase, and we get ourselves a bright spot. So, for constructive interference, if the path lengths traveled are integer multiples of a wavelength, they will meet in phase. So there we go. That's the condition right there. That the path lengths that they travel are integer multiples. Path lengths traveled are integer multiples. Wavelength path lengths traveled have differences of integer multiples. Differences of integer multiples. We want the path lengths to be integer multiples of one another. Then this is what we're going to get. So we can say we've got some path length, R1. And we've got some R2. Difference between those two path lengths are an integer multiple of a wavelength, we got that they meet in phase. if absolute value of R1 minus R2 is equal to M times lambda, they will meet in phase. And produce bright spot, which we call maxima. M is equal to some integer. M is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, dot, dot, dot. There we go. So if n is equal to 0, we'd have that the path lengths are the same then. And what do we get? Constructive interference. If m equals 1 or negative 1, they're different by ultimately one wavelength. M is equal to 2, they're different by 2 wavelengths. And really, writing the plus and minus here doesn't really necessitate this absolute value. I'm going to take that off. Anyways, m is known as, or m is called the order number. And what we can call, and what we can then reference is the different maxima in terms of their m value. We could say the 0th order maxima, the 1st order maxima, 2nd order maxima, 3rd order maxima, and such things. So we call it order numbers so that we can reference which one we're talking about. So this is ultimately like this. If I have another beam, in a sense, or another path, it's like this. We can meet over there in phase, and I can produce another bright spot, where one's undergone 1 or 2 or 3 more oscillations than the other. Meet in phase, good. Where do we get the dark spots? Well, where they are not in phase. Erase this part. So for destructive interference, if the path length difference is, well, what would it have to be here? If one is a half of a wavelength more or less than the other, we're going to get destructive interference. Because if we shift one over by half a wavelength relative to the other, we've got, they're out of phase by pi radians, 180 degrees. And thus, they're completely out of phase, and thus we get complete destructive interference. So a half a wavelength does it, but a full wavelength does not. Full wavelength gives us back constructive interference. But 3/2 would give us back destructive interference because they would still ultimately be out of phase because of that half wavelength shift overall. So the criteria ends up being a little bit different, but we got half integer, the path length difference is say 1/2 a wavelength. They meet out of phase. But again, we don't just want 1/2, but we don't want 2/2. 2/2 is equal to 1. So it's 1/2, 3/2, 5/2, 7/2, so on. So what we can write is condition R1 minus R2 is equal to, we'll say m plus 1/2 times lambda, or again, n is equal to 0 plus or minus 1 plus or minus 2 plus or minus 3, still known as the order number, but this gives us a concise way of relating the path length difference to a condition necessary for destructive interference. Sticking m equals 0, we've got the path length difference is lambda over 2, half of a wavelength. Sticking m equals 1, we've got it's different by 3/2 of a wavelength. M equals 2, 5/2 of a wavelength, and so on and so on and so on. As long as overall there's a half a wavelength difference between their path lengths, we've got ourselves a meet out of phase destructive interference. So we got these two conditions here. Constructive interference, m lambda for the path length difference, and destructive interference, the quantity of m plus 1/2 times lambda for destructive interference. You should note the dark regions called minima. So we've got maxima and minima that we generally discuss in terms of the bright spots, the dark spots, and that's basically it. All right, so what we want to be able to figure out is how can we represent this path length difference? So that takes a little bit more doing. Let's go ahead and try to do that. So, I'm going to use a little bit of an approximation here in terms of how these paths are relative to one another. Now these slits are separated by a very, very small distance. And as long as we keep the screen sufficiently far away, which really, if the separation distance is like a millimeter or even smaller, the screen being far away is not that hard to do. We have that the two beams that meet up are almost parallel to one another. Of course, they can't truly be parallel because they're diverging to one spot, converging to one spot, where they're meeting up and producing interference patterns. But any two paths, as long as the screen distance is sufficiently large comparative to the slit separation, got that they're almost parallel to one another. So very, very small angular separation between them. So let us do this. We can go ahead and draw out a screen here. Take ourselves a couple slits. Let's not do a screen. So we got our two slits here, and I'm going to say that these slits are separated by some distance d. D equals slit separation distance. So we've got that slit separation distance. We're going to say there's some screen way, way far away, much farther away than the actual spacing of this. So I'm not even going to draw it out. But ultimately, two beams or two paths are going to converge somewhere. But since the screen's really far away compared to this, those two beams look very, very near parallel to one another. So let's draw this. Actually, I'm going to draw on the principal axis here. Directly in between the slits, and what we're going to have is this. So we're going to have ourselves some path like this, great, and another path that's parallel to that like this, but really again they're converging because they're going to meet up, but we're going to approximate them to be parallel. So I'm just going to put something here in black. And think about what is the difference between this length and this length, with them converging, well, it'll be the same thing as going this nice right angle here. Little right angle there. That right there is the path length difference delta that they would travel, which is the same as that right there. The difference in the path strap, path lengths. So if we can figure out what this little delta is right there, we can go ahead and start to do some other things. Well, what do we have here? A nice little triangle. Nice triangle, and we've got this angle right here, which I'm going to call the angle theta. So let me take this triangle out, and I'm actually going to rotate it a little bit more than 90 degrees so that it's more looking nice for us. So I'm going to expand it out a little bit, and there's the base, there's our little path length, and there's D. So we've got this D, and we've got this path length difference here, and we've got this other leg over here. That's okay. We've got this angle right there as well. So what can we say about this? Well, we can look at the sine of theta, right? Sine of theta is going to be opposite over hypotenuse, delta over d, which then says that delta is equal to d times the sine of theta. So if we can determine what theta is, and we know what the slit separation is, we can then correlate that with the path length difference itself. And we already know the conditions for the path length difference substantiating constructive and destructive interferences. So we just need to figure out that angle there. Well, how are we going to do that? What happens if we go ahead and we define another angle here? Use a different color. I'm going to say that there's this angle here that the ray makes relative to the principal axis. I'm going to call that some angle phi. So angle relative to the principal axis, that's a nice angle to define, easy to measure. And well, because we have kind of alternate interior angles here, that's going to be the same angle as that. So that's good. That's good. What can we do with this? Well, we can look at some triangles, right? We can look at some triangles indeed. What do we have? Well, we've got this triangle right here, and we've got this triangle right there. So what do we want to do? We want to figure something out with this. I'm going to pull this piece out. So we've got this bigger triangle right here. That, I'm just going to pull it out and draw it out like this so that we've got this angle phi here. We've got 90-degree angle there. And what can we call this? Let's call this some angle gamma, just to call it something. And we have to have that phi plus gamma plus 90 is 180, or phi plus gamma has to be equal to 90 degrees. So we've got phi plus gamma has to be equal to 90 degrees. All right. And what else do we have? Well, in terms of this little triangle here, we've got this theta, we've got this 90 degrees, and we just said, let's call this angle right here gamma. So in terms of this, we've also got this is gamma. Well, theta plus gamma plus 90 has to be equal to 180. So this says then that theta plus gamma is equal to 90 degrees. Well, theta plus gamma is 90, and phi plus gamma is 90. This gives us the conclusion that this angle phi is equal to that angle theta. That is, the angle that the ray makes relative, or the path makes relative to the principal axis is equivalent to this angle here, which then gives us the ability to look at the path length difference itself. So, if we can measure angular separations relative to the principal axis, we're pretty good here. And, again, these slits are really, really close together. This is way exaggerated. So really I can think about shifting things up and just measuring relative to the principal axis from one location. We'll draw that out here momentarily. In the end, for this, we can now write that for constructive interference, maxima occur by d times the sine of theta is equal to m lambda. And minima occur, destructive interference, d times the sine of theta is equal to the quantity of m plus 1/2 times lambda. N is equal to 0, plus or minus 1, plus or minus 2, dot, dot, dot. And the lambda is the wavelength of light. Theta, theta is the angle of the path. Relative to the principal axis. And D is the slit separation. With that, overall, just sort of draw this out. We've got the slits are contained in some little spot right there because they're really, really close together. We've got from this some principal axis, and then we've got some screen to observe the interference pattern on. And make this a little bit long, that's okay. And what are we going to get? Well, we're going to get this. Let's take the blue and say we're going to get some maxima there. Let's say that we're going to get another maxima here, maxima here, maxima there, maxima there, maxima there, and likewise down below. And we want to be able to call these maxima something. And we want to be able to correlate again an angle with respect to them. So this is known as the central maxima. This is m equals 0, central maxima. This would be the m equals 1, first order maxima. First. This would be, for instance, this would be -1. So on, so on, so on, second order maxima, and same thing down on the bottom, down below, we just have above, below, plus and minus. That's how we're going to name the maxima. Now we've got to be a little bit careful because we have order numbers for the minima as well. But just again, focusing on the maxima, what do we have? One occurs along the principal axis. That's where the two path lengths are exactly the same. Then here's where the path lengths differ by one wavelength. and they differ by 2 wavelengths, 3 wavelengths, 4 wavelengths, 5 wavelengths. We'll just go ahead and put it up. This is m equals 5, the 5th order maxima, and we would have some path to that. It's like that. So I'm doing the m equals 5, but each of these would have some path from the slit to that point in space where the interference pattern is occurring. We define this angle right here. I'm going to call this theta. But I want to call it a specific theta because it correlates, number 1, with maxima, and number 2, with the 5th order maxima. So I like to double subscript these thetas. One subscript dictates whether we're talking about maxima or minima. So we use bright and dark. So I'm just going to say theta sub b for bright. And then it correlates again with the 5th order maxima. So I'll call it theta b5. Theta b5 is the angle at which the 5th order maxima occurs relative to being measured from the principal axis. Excuse me. Anywhere I put the screen along this path, I will have that m equals 5 maxima. That's how we dictate it. Theta b5 is the angle at which 5th order maxima occurs. Again, relative to the principal axis. You can have a theta b1, be a much smaller angle. That would go with this. B is for bright, and we got maxima. Well, likewise, we've also got these spaces in between. The spaces in between are dark spots. Those are minima. So we can also look at that. Right here, I'm going to go ahead and erase this a little bit. We've got this. And I want to use a black in this case. So right here, we've got this minima here. This would be m equals 0. Minima, the 0th order minima. Because n equals 0 gives us, putting 0 gives us half of a wavelength difference. There is no central minima. It's one central maxima. Everything's symmetric about m equals 0 maxima. There's m equals 0 minima, and then this would be m equals 1. This would be m equals 2. This would be m equals -1, and so on, and so on, and so on. And what can we do with this? Well, let's go up here to, say, m equals 3. The 3rd order minima, and there's some path that goes from where the slits are to that location. A little sloppy there. Yes, even sloppier. That's okay. Just go ahead and put that in. Hard to draw straight lines for me sometimes. That's okay though. Hopefully you get the picture here. Okay, now I'm just messing things up. I'll stop. We've got this angle here. Got some angle theta at which that path produces that n equals 3. I don't just want to call it some 3. I want to make sure that I'm regarding it in terms of destructive interference, or dark spots. So I'll call it D3. Theta D3. D goes with destructive or dark, and 3 means it's the 3rd order. Theta D3 is the angle at which 3rd order minima is produced. Great. D dark. Constructive interference. So that's great. We got all these order numbers that pertain to the bright spots and the dark spots, constructive and destructive interference, and give us some angular association with respect to the principal axis. Everything's measured relative to that. What we also want to be able to do is look at the locations of these particular bright and dark regions on a screen that's some distance away. So let us not draw in that, because that will get really messy looking really quick. We'll redraw something really quick. Take our little slits there, take some principal axis, take some screen to capture the pattern on, to be able to see it, view it, if you will. Got our little slits there, and I'm going to kind of broaden this out a little bit, make it bigger, exaggerated in a sense. So got our central maxima there, then the zeroth order minima, first order max, first order min, second order max, second order min, third order max. That's alternation between them. That's good, but then we're also going to do this, and we're going to say that there's some quantity L, which is the distance from the slits to the screen, distance from really the slits to the central maxima, if you will. Screen distance there. And let's just look at one of these. Let's say, you know what, I want to know, where does this particular third order maxima occur? Let me try to draw a straight line with this one. Whoa, not too straight, but not too crooked either. So we got ourselves m equals 3 max right there. What I want to know is how far away is that from the central maxima? So we can name some distance here. The distance from really the principal axis to this location, and call this some YB3. YB3 is the distance that the third order maxima occurs relative to the principal axis. YB3 is the distance along the screen from the central maxima to the third order maxima. So we've still got the B for bright and 3 for the third order. So still subscripting things with some way of determining these different things here. We've got this angle theta right here. Just a little red, why not? What theta is that? Right, that's got to be theta B3. Angle at which the third order maxima occurs at, relative to the principal axis. Well, look at this. We've got this distance right here. Everything is measured relative to this, so this is like a 0 in a sense. So this distance is YB3. We've got this is L, the length, and there's theta right there. So what can we do with that? We've got a nice tangent going on. We can say that the tangent of theta B3 is equal to opposite over adjacent. We've got YB3 divided by L, or YB3 is equal to L times the tangent of theta B3. there we go. There's the distance that the third order maxima is from the central maxima. What does it depend on? It depends on theta b3, of course. It depends on the screen distance. The closer the screen is, well, the shorter the distance between the central maxima and, well, that particular interference position. But the further we are away, the larger the separation. Right? That's something that we can control, right? We can put the screen at different distances away and produce particular spatial separations between successive maxima, for instance, so that we can actually see the patterns. There we go. That's it. So in general, we have that y is equal to L times the tangent of theta, where this can be for a dark spot in any order or for a bright spot in any order. If we wanted to know, for instance, 0, if this is the first order minima, or min, and equals 1. Because this one's 0, right? The first one's actually 0, gotta be careful with that. This is occurring at some angle theta d1. And we would have this distance right here, y d1 is equal to L times the tangent of theta d1. You can do this with anything. We got that in general. The thetas we figure out by the wavelength of light and the order number itself, and the slit separation. Here we go. All right, so what we'll do is we'll look at a little problem that kind of looks at some of this stuff here. But that's in another video. This one was a long one. Whew, I'm sweating. Have a good day. Take care.